When we're solving mirror problems using calculations, we need to be really careful about the signs that we're using because each of these variables has its own sign convention based on the type of mirror we have or the type of image. And when we put those variables into our equations, shown down here on the left, we're going to get really different results based on whether we use a positive or a negative number. So it's really important that you're aware of those sign conventions and you're using them correctly. The first one is for the focal length. This is defined based on the type of mirror that you have. If you have a concave mirror, that's the type that's curving inwards, our focal length is defined as positive. Whereas if you have the convex mirror, that's the opposite. It's the one that's kind of curving outwards. That has a negative focal length. So that's just something that you'll be able to tell from the question. It will tell you the type of mirror that you have, and that will determine whether you use a positive for your focal length or a negative. Then we have our object distance and object height. Both of those are always defined as positive. That's because we're always going to be drawing our object in front of the mirror on the left-hand side, somewhere over here, and we're always going to be drawing it pointing upwards in that kind of positive section of our drawing. So both of those are going to be defined as positive. Now, these other variables are going to change depending on the type of image that we have. So firstly, for the distance that we get. The distance of the image depends on whether our image is real or virtual. If our image distance is positive, that's telling us that our image is real. On the other hand, if our image distance is negative, that's telling us our image is virtual. So when you put in your numbers, if it comes out as positive, that's telling you, oh, I have a real image. If it comes out as negative, that's telling you I have a virtual image. The height is similar. Whether it's positive or negative tells us something about our image. This time it tells us the way up it is. So if our image height is positive, that's telling us our image is upright, so the right way up. On the other hand, if our image height is negative, that's telling us our image is inverted, so it's going to be upside down. Lastly, we have our magnification. This may be positive or negative based on whether our image is the right way up or not. The important thing about the magnification is that it can tell us how big our image will be. If our magnification is greater than 1, this is telling us our image is bigger than our object. If it's equal to 1, that's telling us our image is the same size as our object. Finally, if our magnification is less than 1, that's telling us our image is smaller than our object. So you can see each of these has its own sign convention, and based on what you put in, you'll get something different out. So it's very important that you're aware the type of mirror that you have and the type of image, and you're putting in those signs correctly so you can get the correct answers out in the end. In this problem, a student places an object of height 15 centimeters in front of a concave mirror, and it creates an image at a distance of 50 centimeters in front of the mirror. The mirror has a focal length of magnitude 25 centimeters. We're going to be solving this problem using the calculation method. And part of the calculation method is getting the sign conventions correct for each of our variables. That's going to be really important for our numbers coming out correctly in our equation. So first, we're going to read the information from the question, fill those out into our work table, and think about the signs as well. So firstly, it tells us the object has a height of 15 centimeters. We can add that in our work table. The object height is always defined as positive. So that's just going to be 15 centimeters in there. It's a concave mirror. That's telling us the focal length is going to be positive. So we can add a positive there as a reminder. It then tells us it creates an image at a distance of 50 centimeters in front of the mirror. So this is telling us about our image distance, DI. It's going to be 50. And because it's in front of the mirror, that's telling us it's on the left-hand side, somewhere over here. That's going to be a positive image distance because it's going to be a real image that we can see. So we can put that in here. Then we're told the focal length is 25 centimeters. Again, since it's a concave mirror, we know that's going to be positive. So our focal length is positive 25. Those positives you don't need to include in your answer because it's assumed they're positive. You can if you want, it's up to you. Okay, so these are the variables provided for us in the question. Now we need to figure out which equation we can use first to start solving and finding some of our unknowns. So I'm going to look at my 3 equations and figure out which variables I have already and what I'm trying to find. So far, I know the focal length, so I can highlight that to say I know what that is. I know the distance of the image, so I can highlight that here, and it also appears in this equation here. And I also know the height of the object, so I can highlight that there. So right now we can see we have just one equation here where we have only one unknown. So we can solve this equation now. The other 2 equations here and here both have 2 unknowns, so we can't solve those yet. So we're going to solve that first equation to start with, and then we'll be able to use what we find in the other equations. So let's get started with solving that one. First, I need to rearrange it since I'm trying to find the distance of the object. So to do that, first I'm going to subtract 1 over the distance of the image from both sides. So I'll do that now. That's going to end up with 1 over the distance of the object is equal to 1 over the focal length minus 1 over the distance of the image. And then finally, to get the distance of the object on its own, right now we have the reciprocal. So I'm going to need to take the reciprocal again, which means 1 divided by. So to get the distance of the object on its own, I'm going to need to do 1 divided by 1 over f minus 1 over the distance of the image. Now all I need to do is put my numbers in. So we can do that here. Distance of the object is equal to 1 divided by 1 over the focal length from the question was positive 25. Make sure you include the sign. So I've just put 25 since it's positive. If it was negative, I'd need to include the negative there. Minus 1 over the distance of the image, which from the question was 50. Again, that's positive. So there's that. And I can put that into my calculator. That's going to give me an answer of 50 centimeters. And I got a positive answer. That makes sense since the distance of the object is always defined as positive. So that's good that I got a positive answer. So in this one, we're saying actually the distance of the object and the distance of the image are equal. They're the same here. So we now know our distance of the object. So I'm going to highlight that in my equations to show that we know it. We know that this equation is now done. We figured out everything we can from that. And we now know the distance of the object there. So we can now see this equation has just one unknown left to solve. So this one is now solvable. So let's do that one next. So here's our equation. Magnification is equal to negative distance of the image divided by distance of the object. And I'm trying to find the magnification. So it's already arranged in the correct way. I just need to put my numbers in. So magnification is going to be equal to negative distance of the image, which was 50, divided by distance of the object, which was also 50. That's going to get me an answer for the magnification of -1. There are no units with this answer since distance is centimeters, distance is centimeters, centimeters divided by centimeters cancels out. So there's no unit on that. The magnification is just -1. The negative is really important, so make sure you notice that and write it down. Okay, final thing that's missing is our height of the image. Let's go and have a look in our equations. We now know magnification. So this equation on the right is done. This equation on the left, we can now use to find the height of the image. So I'm going to write that equation out and then rearrange it. So we have magnification is equal to the height of the image divided by the height of the object. I want to rearrange this to get the height of the image. So I'm going to multiply by height of the object on both sides to get height of the image is equal to magnification multiplied by height of the object. Then we can put in our numbers. Magnification is -1. Height of the object was 15 centimeters from the question. So that's going to get me an answer for the height of the image of -15 centimeters. So I can fill that in my work table there. Okay, great. We found all our missing variables. Final thing to do is answer these 3 questions. So the type of image formed, since distance of the image is positive and the image was in front of the mirror, the type of image is going to be real. The image size is the same as that of the object. Both were 15 centimeters high. So we have the same size. Another thing we can look at for that is the magnification and see that it's 1. It's -1, but it's still 1. So that's showing us the multiplicative factor was 1. It's the same size. Lastly, for the orientation, since our height of the image was negative and our magnification was negative, that's telling us it's going to be upside down or inverted at the end. So we've just solved this problem using the calculation method. However, we can now check our answer using the visual method by drawing. So let's just do that quickly to do a nice verification of our answer. So from the question, it was 15 centimeters tall. And we can actually use what we calculated here to check. So we had 15 centimeters high at a distance of 50 centimeters. So 1, 2, 3, 4, 5. That's 50 centimeters away. And it's going to be 15 centimeters tall. So 1.5 squares tall, since each square is worth 10 centimeters. Our focal point is at 25 centimeters away. And since this is a concave mirror, that focal point is going to be in front of the mirror here. Okay, next we'll draw our rays. We've got 2 rules to use. One of those rules is that a horizontal ray is going to travel through the focal point when it gets reflected. The other rule is that a ray that travels through the focal point is going to be reflected horizontally. And we can see that our rays cross down here. So that is going to be where our image is formed. And now we can see here, yep, it's at the same distance away, 50 centimeters, 5 squares. It's the same height, it's 15 centimeters or 1.5 squares high. And it's inverted, it's upside down. We can also see it's on the same side of the mirror as the object, so it's real. So here, it's just nice to be able to do this and check our answers to make sure that they look correct and check if we've made any mistakes. In this question, a student places an object of height 40 centimeters at a distance of 35 centimeters in front of a convex mirror. The mirror has a focal length of magnitude 69 centimeters. And here we're solving using the calculation method. So first, we're going to look at our question, take those numbers and get them into our work table, whilst being mindful of the sign conventions, whether we have positive or negative for each of those. So firstly, we're told some information about the object. The height is 40 centimeters and the distance is 35 centimeters. Both of those, distance and height of the object, are defined as positive. So those are both just positive there. So we've got 35 for the distance. And for the height, we have 40. Then we're told the focal length is 69 centimeters. Now, for a convex mirror, which is what we have here, focal length is defined as negative. So we're going to put that in here as negative 69 centimeters. Okay, awesome. So we've got all our known variables in our work table now. Let's take a look at our equations and figure out what our unknowns are and what we can solve for first. So we know focal length, that appears here in our equation. We know distance of the object, that appears here, and it also appears here. And we know height of the object, which appears here. So looking at our equations, this one is ready to be solved because we just have one unknown. The other two equations still have two unknowns and can't be solved just yet. So we'll solve the first equation, and then we'll use what we find to solve the others. First, I'm going to need to rearrange it to get distance of the image on its own. So to do that, I'm going to subtract 1 over distance of the object from both sides of my equation. So I'm going to get 1 over distance of the image is equal to 1 over the focal length minus 1 over the distance of the object. And now to get distance of the image, because we have the reciprocal or 1 over to start with, I'm going to need to do 1 divided by both sides of my equation to get distance of the image. So distance of the image is going to be equal to 1 divided by 1 over the focal length minus 1 over the distance of the object. So I can now put my numbers in for that. Distance of the image is equal to 1 divided by 1 over the focal length, which I got negative 69 for. Again, being careful with my sign conventions. And then I'm subtracting 1 over the distance of the object, which was positive 35. And if I put that into my calculator, I'm going to get an image distance of negative 23.2. So I can pop that up here. That's in centimeters. So we now have our image distance. So this equation is done since we've found everything in there. We also now have the image distance in this equation. So we just got one unknown left here. So let's solve this equation next. I'm going to write out the equation again. Magnification is equal to negative distance of the image divided by distance of the object. And I'm trying to find the magnification, so that's already arranged correctly. So all I need to do is put in my variables. So the distance of the image, I calculated as negative 23.2. So it's going to be negative from the equation and then negative 23.2 divided by the distance of the object, which was 35. Here, since we have negative of a negative, that becomes positive. So we have 23.2 divided by 35. And that gives us a magnification of 0.666. You can fill that in here. Notice how that's positive. And again, that doesn't have a unit. Now we have our magnification. That equation's done with. And finally, we can use our magnification in our last equation to find the height of the image. So let's do that now. I'm going to write out that equation over here. Magnification is equal to height of the image divided by height of the object. And I need to find height of the image on its own. So to get rid of the height of the object on the bottom, I'm going to multiply by height of the object on both sides. That's going to give me magnification times height of the object is equal to height of the image. So all I need to do now is put my numbers in again to get the height of the object. Magnification, I calculated as 0.666 multiplied by height of the object, which was given as 40 centimeters. And I can pop that into my calculator to get a height of the image of 26.6 centimeters. Which I can add in here. Okay, awesome. So we've used those equations to calculate all of our variables. Last thing to do is answer these questions and figure out what these numbers actually mean. So the type of image formed, this is told by the distance of the image. Since it's negative, that's telling us we have a virtual image formed. The size of the image can be found out from the magnification. Since the magnification is less than 1, it's telling us our image has gotten smaller. So our image is smaller. We can also tell that by looking at the height of the image and the height of the object and comparing those directly to see that it's gotten smaller. Lastly, the orientation of the image. That can be told from whether the height of the image is positive or negative. Since it's positive, that's telling us it's the right way up, or in other words, it's upright. Another way to find that is from the magnification, which again is positive, showing us that it's upright. So that's how we solve the problem using the calculation method. Another thing we can do is use the visual method just to verify and check our answers to make sure that they look about right. So let's do that now just to check. So our object has a height of 40 centimeters at a distance of 35 centimeters. So 10, 20, 35 centimeters distance and 10, 20, 30, 40 centimeters high. That gives me my object over here. My focal length was negative 69 centimeters, which is telling me it's 69 centimeters and it's behind the mirror over here. So 10, 20, 30, 40, 50, 69. It's just going to come right before that line there. So around about there for my focal length. And now I can use my 2 rules for drawing ray diagrams for mirrors. The first one is that if I draw a line that is horizontal, parallel to the horizontal axis, it's going to pass through the focal point when it's reflected. However, it can't actually go over here since it's a reflective mirror. It can't go through, so it gets reflected back such that if we extrapolate the line back, it would go through the focal point over here. So if my line would come from over here, then I can draw my ray coming out that way. My other rule is that if my ray goes through the focal point, it ends up coming out horizontal, parallel to the horizontal axis. Again, it can't actually go through the focal point because it can't get through the mirror. It gets reflected off of it, but it goes as if it were going through the focal point. So it goes in that direction as if it were going to go through the focal point over here. And it gets reflected parallel to the horizontal axis like that. So here we can see our rays do not cross, which means that we need to extrapolate them back behind the mirror. Because if we imagine our eye over here looking into the mirror, we see this ray coming out at us, and we see this ray coming out at us, and we visualize where they came from. So this red ray, we visualize coming from back here. The blue ray, we visualize coming from back here. So let's draw that one on. Okay, so we can see where we're visualizing those rays coming from. So we can see where these cross, which is around about there. We can draw on our image, which will be around about there. Okay, now we can do some checks. So for the height of the image, we've got about 1025-ish. Looking at our answers, we got 26.6. That looks close enough. For the distance, we got 10, 20, yeah, around 25-ish again. Checking our answer, we got 23, so that's about right. Then we can check the size. It looks smaller than the original. That makes sense because our height was smaller and the magnification is less than 1. It's upright, which is why our magnification and our height of our image were both positive. And lastly, it's behind the mirror and it's virtual, which is showing us that our distance of the image is negative. So everything matches up from our visual method and our calculation method. So that's just a nice way to check that we did it correctly.